In this video, we are continuing our discussion of section 11.5. In this video, we are going to cover the distance between a point and a plane. So notice my plane there in orange, and then I have my point up here. Let me make it a little more obvious. It's here in black. So there's the point we're looking at, and we're trying to find the distance between that point and its plane. So what we're looking at here when we're talking about distance between a point and a plane, we're talking about the perpendicular distance. So that is actually a distance d here. Now, I do want to create a vector here to kind of help us out. We are going to create a vector from this point on the plane to the point off the plane. So there's my vector. And what we're going to think about is projecting this vector, because we have this vector, we have the point off the plane, and we can find a point on a plane. If I project this, remember this is like sunshine coming from this way, right? So if it gets projected, I would actually get this vector here. But if I want the distance of that vector, it's the magnitude. And then if you remember, the magnitude of a projection is what we call this component. So that is our actual distance. Remember, the projection is this vector right here, because that's what the sun would project over this vector going this way onto the green vector. We'd have this vector. If I want the distance, then it's just a comp. Now, if you remember from a couple sections ago, the component scalar of our projection is defined this way. So if I wanted to find the distance of that, I would just actually plug in those vectors instead. So I am taking the component scalar of, okay, this is P naught P, that's that black, this vector, this black one here, projected onto N, my normal vector of my plane. Right? If I follow this formula, this is P naught P vector, dotted with my normal vector, and we have divided by our magnitude of our normal vector. Now, this is distance, right? That's what we just called that. That magnitude of the projection is d. And what we're going to do is we keep our absolute value. And if we think about this, using everything that we have, this is p and p naught. We can create that vector by subtracting. We know we can call n, a, b, and c. So when we dot product these things, we're going to get a times x1 minus x naught plus b times y1 minus y naught plus c z1 minus z naught. That's just definition of dot product by the way those are defined, right? The magnitude definition, right, will be square root of a squared plus b squared plus c squared. That's magnitude. And then we have one other way we can write this. That was standard form. We could write this in general form as well. Sorry, don't know why it zoomed in like that. We get a x1 plus b y2, or 1, plus c z1, and then everything else can be combined for that d, divided by that same definition. So if, let's sum this up real quick, because we do have this formula. We wouldn't have to derive this ever again, but we could use it if I need the distance between a point and a plane. Well, the top is just my plane, that is the definition of the plane, with the point plugged in. That's all it is. X1, Y1, and Z1 came from here. So if I was trying to find the distance, I would just plug the point into the plane, and then I would divide it by its magnitude of its normal vector. Pretty nifty, pretty sweet the way it works. For me, I think as I went along, I just think of the formula, and I keep forgetting that this is why. The formula is okay. I actually haven't had it come up a whole lot in my life, but it does come up every once in a while. So it's a good formula to have.